Welcome to Catch This. My name is Trudy Ray. Public awareness of human immunodeficiency virus, or HIV, began in the early 1980s when separate clusters of infected individuals were identified in Los Angeles, San Francisco, and New York. These individuals all shared a group of symptoms later named acquired immunodeficiency syndrome, or AIDS. AIDS is a disease state that is characterized by a profound susceptibility to infections and cancers that don't typically affect people with a competent immune system. Even though the quest for a vaccine to prevent and/or cure HIV infection began immediately, nearly half a century later, we still don't have one. Why is that? This video is the first in a two-part series about HIV. In this video, I will discuss the reasons for why we don't have a vaccine, and in the next episode, I will tell the story about how HIV emerged in humans. Don't go away! There are multiple hurdles that have prevented progress in vaccine development in the field of HIV. The most glaring obstacle is the fact that HIV integrates into the host genome and becomes part of that person's DNA for life. After entering a host cell, the viral-encoded reverse transcriptase enzyme converts the HIV RNA genome into DNA, which is then inserted into the host genome by another viral enzyme named integrase. Each new round of replication of the host's DNA also produces new copies of the inserted viral genome. Newly replicated HIV DNA is transcribed into RNA, which then gets packaged into newly synthesized viral particles that are assembled with the help of a viral enzyme named protease. Taking this sequence of events into consideration, with the caveat that most vaccines prevent disease but not infection, any potential HIV vaccine would probably exert its function too late. In other words, a vaccine that induces an immune reaction to a virus that has already infected the host might not be as effective if the virus has already integrated into the host genome. After infection and integration, HIV persists in a pool of cells collectively known as the HIV reservoir. These cells consist primarily of a certain subtype of T cells known as T helper cells, but can also include macrophages, microglia, and astrocytes. HIV reservoir cells are capable of increasing in number, and it has proven extremely difficult to identify and eliminate such pools of cells. Even the small group of HIV-infected individuals known as elite controllers, who are able to maintain suppressed viral levels without antiviral medication, retain a low frequency of intact integrated HIV DNA copies in their peripheral T helper cells. An additional hurdle in HIV vaccine development has to do with the high rate of mutations that occur during viral replication. Unlike other enzymes of its type, HIV reverse transcriptase does not have a proofreading mechanism, meaning that it introduces multiple errors into each new strand of DNA during each round of replication. But what's more is that each viral particle contains two copies of single-stranded RNA, and reverse transcriptase often switches back and forth between the two strands, thus producing DNA copies that are recombinants of the original two RNA templates. Combined with the rapid rate of replication of HIV, these factors lead to the generation of infinite numbers of viral variants in any given infected person. To demonstrate, consider the following numbers. The rate of mutation of HIV reverse transcriptase is about 0.000034 mutations per nucleotide per replication cycle. That doesn't sound like a lot, but the HIV genome is about 10,000 nucleotides in length. And an infected person produces about 100 billion new virions each day. It then follows that an infected individual can generate about 34 billion viral variants in a single day. Designing a vaccine that induces broadly neutralizing antibodies and/or T cells to so many different variants is daunting. The immunodeficiency aspect of HIV disease stems mainly from the fact that HIV infects and kills the cells that are central to the adaptive immune response. Although HIV also infects macrophages and dendritic cells, As the infection progresses, the virus primarily targets T cells that harbor CD4, a cell surface protein that aids HIV entry into cells. These CD4 positive T cells, also known as T helper cells, mentioned earlier, are essential for activating the adaptive immune response because they produce signaling molecules that stimulate B cells to produce antibodies and cytotoxic T cells to kill pathogens and infected cells. As more and more T helper cells are infected and killed, they progressively decline in number. Because there are insufficient T helper cells, B cells are not stimulated to make antibodies, and cytotoxic T cells are not activated to attack invading pathogens, a situation that leads to increasingly compromised immunity. So, to recap, here are some hurdles that have prevented development of an HIV vaccine. HIV integration into the host genome, the existence of an HIV reservoir, the high rate of mutation of the virus, and the fact that HIV infects T cells, which are essential for adaptive immunity. The development of antiretroviral therapy, also known as ART, in the mid-1990s led to a major turning point in the HIV pandemic because it marked the end of HIV infection as an inevitably accelerated death sentence. ART consists of a combination of drugs that inhibit the function of various factors involved in the viral replication cycle. These factors include proteins that facilitate viral binding and cell entry, and enzymes like reverse transcriptase, integrase, and protease. When properly adhered to, ART reduces the amount of HIV in the body to an undetectable level, thereby decreasing the risk of transmission to others while greatly increasing the life expectancy of the patient. In the meantime, efforts are still underway in the field of HIV vaccine research, particularly with the advent of artificial intelligence, which has provided a variety of new tools that aid in vaccine design. AI-assisted predictive modeling can be used for various purposes, including clarifying the mutational pressures of HIV, estimating immune responsiveness to various drug delivery systems, identifying broadly neutralizing antibodies, and managing the complex workflow of clinical trials. However, considering the numerous barriers described in this video, which are not all-encompassing, any promise of an HIV vaccine should be perceived with caution and a healthy dose of skepticism. That's it for today. Thanks again for listening. Please subscribe. My name is Trudy Ray, and I'll see you next time on Catch This.